A warm welcome to the 10th lecture on the subject of wavelets and multirate digital signal processing. Recall that in the previous lecture, we had established the intimate connection between the scaling function, the wavelet function, the continuous time scaling function, the wavelet functions, and the two channel filter bank about which we had been discussing in a few lectures before that. Towards the end of the previous lecture, we were convinced that there is an intimate connection between designing a two band filter bank and designing a multi-resolution analysis. In fact, the connection is so strong that when one knows the impulse response of the low pass filter in the filter banks that we have been looking at, one can by iterative convolution obtain the scaling function, and having obtained the scaling function, one can obtain the wavelet function. So, it is a very powerful reason to study the two channel filter bank in great depth, and that is exactly what we intend to do today. Let me put before you the theme of the lecture today. So, today we intend to talk about the Z domain analysis of the multirate filter bank, and to do that we shall begin by considering the basic operations of the multirate system, namely downsampling and upsampling. The rest of it is known to us from a basic exposure to discrete time systems, but how to deal with multirate operations is what we need to understand much more carefully in the next few minutes. So, let us once again draw the structure of the two channel filter bank, which we have been looking at in some of the previous lectures. Recall that the two channel filter bank has an analysis component and a synthesis component. We had given the following nomenclature for the analysis and the synthesis side. I shall just recapitulate that. So, on the analysis side, we have two filters, the low pass analysis filter and the high pass analysis filter, followed by downsampling operations. On the synthesis side, we have first the upsampling operation, followed by the synthesis low pass filter and the synthesis high pass filter. And you will recall that the outputs of these two were added, and this constituted the overall output. So, we have the input here and the output here. To recall, this is going towards the ideal discrete time low pass filter with a cutoff of pi by 2 on the normalized angular frequency axis, and so is this. This is going towards the discrete time ideal high pass filter with a cutoff of pi by 2 again, and so is this. This is what we call the analysis side of the filter bank up to here. And this is what we call the synthesis side. When I mark this, I mean all this. So, maybe we should put a dotted boundary around. So, this is all the synthesis side and this is the analysis side. Anyway, with this little recall of what we did in the previous lecture, let us identify what it is in this filter bank which is unusual, which is beyond what one normally is exposed to in a basic course on discrete time systems. If you look at it carefully, there are two unusual blocks here and they are the downsampler and the upsampler. So, the unusual or the new blocks the downsampler and you know what the downsampler did. When you had a sequence indexed by the integers, so let us say it is indexed by 0, 1, 2, 3, 4, 5 and so on, and of course, minus 1, minus 2, minus 3 and so on this side. The downsampler lets the 0 sample go to the point 0, the 2 sample to the point 1, the 4 sample to the point 2 and so on so forth. And on this side the minus 2 sample comes to the point minus 1 and so on so forth. So, in a certain sense the downsampler is both a remover of some samples and a compressor of the remaining samples. There are two steps in downsampling if you think about it, and we shall in fact analyze the downsampler treating it as a cascade of two steps. So, to state it clearly, a downsampler first kills some samples. So, for example, if I go back to the same indexing 0, 1, 2, 3, 4, 5 and so on here, and minus 1, minus 2, minus 3, minus 4 and so on there, then 0 is as it is, 1 is reduced to 0, 2 is as it is. So, when I write the number in brackets, what I mean is this sample is brought forth as it is, and when I write 0 here, what I mean is this sample is made 0. So, this is made 0, 4 as it is, 5 is made 0, minus 1 made 0, minus 2 as it is, minus 3 made 0, minus 4 as it is, and so on so forth. So, this is the first step. The second step is to compress. So, it first kills some samples, then compresses the resultant. So, you have 0 where it was, then a 0, 2 where it was, and then a 0, 4 where it was, and then a 0 and so on and so forth here. You have a 0 in place of minus 1, then a minus 2 where it was, 0 in place of minus 3 and so on and so forth here. And the compression brings 0 to the point 0, this to the point 1, 4 to the point 2 and so on and so forth. And here it brings minus 2 to the point minus 1 and so on and so forth. So, there is a so called compression taking place. a removal of the unwanted zeros. Now, when we do a Z-domain analysis of this, we shall do it precisely in these two steps. Let us, before we proceed to the Z-domain analysis, look at the second unusual block here. So, the second unusual block is the upsampler. And we have denoted upsampler by up arrow followed by 2. And you know what the upsampler does. If you have a sequence indexed by 0, 1, 2, 3, 4, 5 and so on and so forth, and of course, to continue -1, -2, -3 and so on and so forth on this side, the 0 sample goes where it is to 0, the 1 sample goes to 2, the 2 sample goes to 4, the -1 sample goes to -2, the -2 to -4 and so on and so forth. So, what we will do is we will put these in brackets now, and we insert zeros in between. So, in other words, we expand in some sense. An upsampler also expands in some sense. So, some people like to call it an expander also, because it in some sense outdoes this last step that a downsampler does. You know, if you think about it, this last step which a downsampler does, namely compresses by removing zeros, is outdone by the upsampler. We should make a note of that, it is important. The upsampler outdoes the last compression step of a downsampler. Hence, it is also called an expander. Now, I must emphasize that the upsampling operation is invertible. So, even the original sequence is unaffected by the process of upsampling. You can get back the original sequence after upsampling it. The same is not true of downsampling. When you downsample, you lose some information forever. So, in a certain sense, you know, downsampling first, as I said, kills some samples and then also compresses, in some sense covers up that killing part, if you want to call it that, by removing evidence of the zeros that have been created. What the upsampler does is to put back the zeros where they were, as if you are recreating the evidence of killing, in a lighter vein of course. Whatever it be, the upsampler takes you from a lower rate system to a higher rate system, and the downsampler takes you from a higher rate system to a lower rate system. So, when you downsample, you are actually changing the effective sampling rate. You know, if you think about it, in downsampling, what are you doing? You are retaining 1 out of every 2 samples. And in principle, what time you allocate to processing each of these samples after downsampling is up to you. What is practically done in most discrete time systems is when downsampling takes place, one allows more time to process samples after downsampling. So, in a certain sense, that downsampling and upsampling operation is taken care of by having different clocking rates at different points in the system. You know, what we are saying in effect is the same system has different effective sampling rates at different points. And to emphasize this point, let us go back once again to that 2-channel filter bank that we drew a few minutes before. You know, if you look back at this 2-channel filter bank here, what we are effectively saying is that there is one sampling rate operating here at the input, and the same sampling rate operates here at the output. However, although the sampling rate here and the sampling rate here, which are the same, also operate after these filters and before and after these filters, they do not operate here, you know. So, at this point, after the downsampler and before the upsampler, and after the downsampler here and before the upsampler, we have effectively a different sampling rate. In fact, the sampling rate here is in principle 1/2 of the sampling rate here. And that is why this is called a multirate system. Now, it is clear why we are talking about multirate systems. We have two different sampling rates in the same system. Now, one can generalize this. You can have more than two sampling rates in the same system. In fact, you know, you might have different kinds of downsampling and upsampling operators. So, let us expand our view in that sense now. So, in general, one could be talking about upsampling and downsampling by a factor of m, so to speak. And that is not too difficult to understand now that we have written down what downsampling by 2 means and what upsampling by 2 means. So, let us write it down. Downsampling by m in general. Which of course we denote by down followed by m. So, let us again take an example for clarity. Suppose we take m equal to say 5, to bring in some variety. So, I have these samples here 0, 1, 2, 3, 4. Now, what I am writing here, please remember, are the indices of the samples, not the values of the samples. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 and so on. And similarly, on this side -1, -2, -3, -4, -5 and so on. What do we do in downsampling by a factor of 5? The first step is to kill some of the samples. So, the 0 sample is kept where it is, the 5 sample is kept where it is, the 10 sample is kept where it is, the -5 sample is kept where it is, but all the other samples, the 1 sample, 2 sample, 3 sample, 4 sample, the sample number 6, 7, 8, 9 are all reduced to 0. So, also -1, -2, -3, -4, all of these are reduced to 0. So, this is the killing step, so to speak, and then the compression step. So, the compression step would bring the 0 sample to the position 0, the 5 sample to the position 1, the 10 sample to the position 2, the -5 sample to the position -1 and so on and so forth here. And remember, there are zeros in between here which are simply thrown away. Zeros thrown away. So, now we understand how to generalize downsampling. In a similar way, we can generalize upsampling. So, suppose we have upsampling by m. Which we denote up arrow followed by m. And once again, for variety, let us take the example of m equal to 7. So, you have this sequence 0 with indices, I mean 0, 1, 2, 3, 4 and so on and so forth, and minus 1, minus 2, minus 3 and so on and so forth. Here, when you upsample by 7, the 0 sample goes where it is, to 0. The 1 sample would go to 7, the 2 sample to 14 and so on and so forth. The 3 sample to 21, the 4 sample to 28 and the minus 1 sample would go to minus 7, minus 2 to minus 14 and so on and so forth. And of course, in between, so I will put brackets around these just for clarity here. In between, you would insert zeros. So, how many zeros would you insert here? 6 zeros. Here too 6 zeros in between. Here also 6 zeros and so on. So, this is upsampling by a factor of 7. We understand now how we can generalize both downsampling and upsampling. And now, what we need to do is to analyze these operations from a transform perspective. So, in the transform domain, which transform? Of course, we will first begin with the Z transform, because it is easier to understand the effect in the Z domain and then go into the frequency domain by substituting Z equal to e raised to the power j omega. Now, you know, it is easier to understand the effect of upsampling, in fact, by a general factor of m in the Z domain. So, let us begin with that. Let us consider a general factor of m, upsampling by m most generally. What do we do when we upsample by m? That is easy. You see, the original sequence is x of n. So, this is the input. After upsampling by m, let the sequence become x u of n. Now, we can write down x u of n explicitly in terms of x of n. In fact, instead of doing that, let us straight away go into the Z domain. Let us consider the Z transform of x u n. That is easy. Summation n going from minus infinity to plus infinity, x u n z raised to the power minus n. And the only catch is, among all these n's, only those n's have a non-zero sample which are multiples of capital M. And therefore, we can rewrite this summation here as summation again, let us say k going from minus to plus infinity, x of k. Now, remember, x of k occurs at the point m times k in x u m, and therefore, here we have z raised to the power minus capital M times k coming up. Now, this is a familiar expression. This is very like the Z transform of x, except that you have replaced z by z raised to the power capital M. So, in fact, there we have a very simple relationship for x u z to x z. Indeed, the Z transform of the sequence x u n, namely x u z, capital X u z, is the Z transform of the sequence x with z replaced by z raised to the power m. Simple. Now, in fact, this also brings before us very clearly the invertibility. So, just as you can say x of x u of z is x of z raised to the power capital M, you can also say capital X of z is x u z raised to the power 1 by m. So, what we are saying in effect is that this operation of upsampling by m, this operation is invertible. Clearly shown here, clearly evident. Whether we look at it in the time domain or whether we look at it in the z domain, this property is evident, the invertibility. Very soon, we shall look at the downsampling operation, and there we shall also see the non-invertibility evident in the z domain. Perhaps not as evident, but evident all the same. So, let us now go to downsampling. Now, as I said, downsampling is a concatenation of two processes. In one process, we kill some samples. In the second process, we compress the so called partially killed sequence. This process of killing some samples is what requires a little bit of effort to express in the z domain. And here we shall not attempt straight away to jump to generalization to any capital M. We shall instead take capital M equal to 2, illustrate the idea and then allow for a generalization to any other capital M. So, let us proceed then with downsampling by a factor of 2 now first. So, here we are. When we wish to downsample by a factor of 2, what we are saying in effect is we are killing every other sample. And how do we kill? One way to kill is to multiply by a killing sequence, so to speak. So, when we consider downsampling by a factor of 2, the first killing step can be viewed as a modulation step. Or multiplication by another sequence, by killing sequence, let us call it. Instead of giving such a violent name, maybe we should call this a window sequence, that is a milder name. What does a window do? A window allows you to see a certain part of the scene outside. In a certain sense, when we retain some samples and destroy all others. That is exactly what we are doing. We are allowing those samples that are retained to be passed through the window and those that are destroyed to be stopped. So, if you wish, we can call this sequence that keeps some and removes the others as a window, but a window periodic sequence. You know, I use the word window periodic sequence because the window sequence name has also been used in the design of finite impulse response filters. And the window periodic sequence has the following pattern. At the point 0, it takes the value 1. At the point 1, it has the value 0, and then periodically thus. And the same on the negative side. Periodically continued on both sides. So, you know, you can think of it as a periodic window where wherever there is a 1, you are allowing the scene to pass, and wherever there is a 0, you are stopping the scene. Let us call this periodic window sequence PWN, where the P is to denote periodic and the W subscript is to denote the window behavior. So, this is a window periodic sequence for downsampling by 2. But you can have a similar window periodic sequence for downsampling by any other factor. So, suppose you were to downsample by m in general. Again, let us take the example now of a variety of m equal to 4 this time. Then the corresponding PWN would be 1 located at 0, then 3 zeros, 1 located at 4, then 3 zeros again, 1 located at 8, and so on this side, and of course 3 zeros and then a 1 and so on this side, periodically continued. Continued this way, continued this way. So, what we are saying in effect is the process of killing, the killing process is essentially multiplication by PWN for the appropriate m. So, if you want to downsample by 2, you have an appropriate PWN, periodic with a period of 2, with 1s located at all multiples of 2 and zeros elsewhere. In general, when you want to downsample by m, you have a periodic sequence PWN with a period of capital M, 1s located at all multiples of capital M and zeros everywhere else. Simple enough. What about the compression step? The compression step can be viewed as an inverse expander, an inverse upsampling step. So, maybe we should say downsampling by m means, or in other words, let us actually put down sequences here. Let us say x n has been downsampled to produce x d n, and that means x n has first been multiplied by PWN. PWN for downsampling by M, for M in brief. And then now look here. You know what we are saying is XDN is here, and I am saying upsample by M, but this way. That means it is an reverse or it is an inverse upsampling operation. Now, if we view the downsampling operation this way, it is again very clear why it is not invertible. This part is invertible, but this part is not, because you cannot divide by PWN. PWN has zeros in it, you can't divide by them. That is another way of viewing it. And of course, this will also get manifested in the Z domain, but subtly. Now, you know, to manifest this in the Z domain, this operation of multiplication by a sequence is difficult to capture in the Z domain. So, what we need to do is to translate this multiplication by PWN into multiplication by other sequences which are easy to interpret in the Z domain. Now, the only convenient multiplication by sequence operation which can be handled in the Z domain is multiplication by an exponential. So, what we need to do is to replace this multiplication by PWN by a linear combination of multiplications by exponentials. How do we do that? So, let me put down our objective a little more clearly. This multiplication by PWN needs to be replaced by Xn multiplied by exponential alpha 1 to the power of n. So, I think maybe I will say multiply by alpha 1 to the power n plus say alpha q to the power n, q such terms. Same Xn. So, multiplication by alpha 1 to the power of n or alpha to the power of n in general is easy to handle in the Z domain. So, the other way of saying it is we need to express PWN as a linear combination, let us say Ck times alpha k to the power n, k going from let us say 1 to q. Now, this is not at all difficult to do. In fact, if you think about it, that is exactly what the discrete Fourier transform does in discrete time signal processing. The discrete Fourier transform essentially expresses a sequence, in fact, a periodic, a time limited sequence as a combination of exponentials. Let me just, to refresh our ideas, put the expression for the inverse discrete Fourier transform before us. So, if you recall, if you have a time limited sequence, let us say it has capital N samples. So, you have, let us give the sequence a name B0 to Bn, or Bn minus 1 to be more precise. So, if this is the time limited sequence of capital N samples, its discrete Fourier transform, if you recall, is essentially capital B of k. Of course, k also running from 0 to capital N minus 1, with capital B of k defined by summation n going from 0 to capital N minus 1 B n e raised to the power minus j 2 pi by n capital N times n k. And then we can reconstruct B n from its discrete Fourier transform. That is easy. B n is 1 by n, summation k going from 0 to n minus 1, capital B of k e raised to the power j 2 pi by n k n. Now, this is true for again n going from 0 to capital N minus 1, but after all, if you recall, what we have here in the discrete Fourier transform expression and in this expression, which is essentially an inverse discrete Fourier transform. Recall that the discrete Fourier transform is often abbreviated by DFT and the inverse discrete Fourier transform by IDFT. In the IDFT, we have exactly the kind of expansion or expression that we desire. We are expressing that limited sequence of capital N samples in terms of its DFT components and exponentials here. So, we have exactly what we want. Now, we can exploit this. You see, what is to be noted here is that although we have talked about a limited sequence, actually you can periodically extend that sequence in capital N, and whatever expression we have here to reconstruct B n from capital B of k. So, B n is reconstructed from capital B of k here, seemingly only at n equal to 0 to capital N minus 1, but even if you apply the same expression for all integer n, you get a periodically repeated sequence. Whatever is between 0 and n minus 1 is periodically repeated in every interval of n successively and before. And that is easily seen if you substitute n by n plus any multiple of capital N here, noting that e raised to the power j 2 pi by n times capital N is 1. Let me do that just for completeness. So, what I am saying is, if we use this expression, the expression summation k going from 0 to capital N minus 1, capital B of k e raised to the power j 2 pi by n k n generates a periodic sequence. So, let us call this expression as a function of n b tilde n. It is very clear that b tilde n plus L times capital N is essentially summation k going from 0 to capital N minus 1 bk e raised to the power j 2 pi by capital N k n plus L times capital N, and this can be simplified. We have k going from 0 to capital N minus 1 bk e raised to the power j 2 pi by capital N k n times e raised to the power j 2 pi L, and this is essentially 1. So, this is essentially 1. So, you may remove this term and leave this, and that is the same as b tilde n. And therefore, what we are saying is, in effect, b tilde n plus L times capital N is b tilde n for all n, and therefore, periodic with period capital N. So, here we have a mechanism for generating a periodic sequence by using a combination of exponentials. Let us exploit that. So, let us now take the case of capital M equal to 2. There it is easy. We need the periodic sequence . Well, 1 0 1 0 and so on, and so forth, and we exploit just one period here. And we construct the discrete Fourier transform of this. That is easy. It is 1 times e raised to the power minus j 2 pi by 2 times, of course, the discrete Fourier transform is a function of the frequency index k. So, this is 0 times k plus 0. So, in fact, b of k is 1. For k equal to 0 and 1. And how do we reconstruct this sequence, the periodic sequence P W n then? For m equal to 2 is reconstructed using the inverse discrete Fourier transform. So, it is summation k going from 0 to 1 bk e raised to the power j 2 pi by 2 times k n, and that is easy to do. That is half summation k going from 0 to 1 times e raised to the power j 2 pi by 2 is j pi k n. So, in fact, let us expand it explicitly. So, that is half. With k equal to 0, it is 1 raised to the power of n plus minus 1 raised to the power of n. And now we are well set. In fact, we are almost there. Indeed, what we are saying is, if you have x n and if you are multiplying this by this sequence and you wish to obtain the Z transform here, all that you need to do is to say, express the following expression, n going from minus to plus infinity, x n into half 1 raised to the power of n plus minus 1 raised to the power of n times z raised to the power of minus n in the z domain, which is easily seen to be summation n going from minus to plus infinity. Of course, half can be brought out everywhere, x n z raised to the power of n plus half summation over all n from minus to plus infinity x n minus z raised to the power minus n. So, we have done our job. Indeed, these are very familiar expressions. This is just the z transform of x, and this is the z transform of x with z replaced by minus z. So, we have this is essentially equal to capital X evaluated at z plus capital X evaluated at minus z multiplied by half. So, we have done our job. Now, all that we need to do is to note that this goes through an inverse upsampler by 2, so to speak. And therefore, if we put these together, we have the final result x n with z transform capital X of z, when it goes through a downsampling by 2, becomes in the z domain x d n with the corresponding z transform given by half x z raised to the half plus x minus z raised to the half. We have done what we wanted to in this lecture. We have established the z transforms of the basic multirate operations in terms of the original z transforms of the sequences. We shall build on this further in the next lecture to carry out the complete analysis of the 2-channel filter bank. With that, then, we conclude this lecture and look forward to the complete analysis. Thank you.